because we're going to start talking about the origin of the solar system. So our solar system really includes the sun plus the 8 planets. Remember, we've made Pluto a dwarf planet, right? So once we get beyond the orbit of Neptune, we get into a region called the Kuiper Belt. So it doesn't really say it here, but the Kuiper Belt is where we see some of these dwarf planets like Pluto and Xena and some other objects that are out in there, right? And then once we go beyond the Kuiper Belt, there's this region called the Oort cloud, where possibly comets originate from this Oort cloud. And then you can see that these numbers that we see on the scale, these refer to astronomical units, or AU. So one astronomical unit is basically 150 million kilometers. That's the distance between Earth and the Sun. So you can see Saturn is about 10 astronomical units away from the Sun. So 10 times 150 million kilometers. The Kuiper Belt is out here about 100 astronomical units. And then when we get to the Oort cloud, we're looking at more than 1,000 astronomical units. For the solar nebula, so everything that's going to form, the Kuiper Belt, the planets, the Oort cloud, they all really form from this solar nebula. So they're really all the same age. So that's the thing, is they're all the same age. And so the solar nebula hypothesis states that there must have been some supernova event nearby that provided the seeds or the heavy atom objects for our solar system, right? And so what happened, the supernova out of the heavy elements began to spin, and gravity started to crunch down and bring these elements together, or these objects together. And eventually we're going to get this idea of conservation of angular momentum. And all this says is basically it's think of an ice skater. When an ice skater is on the rink, they begin to spin slowly, but they have their arms out. In other words, they have a larger radius. But as soon as they bring their arms in, they start spinning faster, right? So this PA is angular momentum, and that cannot change. We know the mass is constant. Whatever we started with, we haven't changed. That's our solar system. But gravity is decreasing the radius. And when we decrease that radius, that means that we have to increase the spin in order to keep this constant, because we can't change that. So as this one goes down, the spin has to go up. It has to go faster. And that's why all the planets, all 8 planets, orbit the sun in the same direction. They all form in the solar nebula. And what's more, since they're all the same age, they're all about 4.6 billion years old. So here is the example of angular momentum and spinning. So we have these planetesimals, right? So this is kind of the solar nebula. It's really rocky. All these smaller planetesimals eventually start crashing into each other and start sticking together and becoming larger objects, and eventually become protoplanets. Eventually the more planets will form. At each astronomical, or at each orbital distance from the sun, you may have 2, 3, or more planets that form, but eventually they're going to crash into each other until there's only one planet. So each planet has to clear its orbital distance around the star here, right? And so basically this is what's shown here. So we have all this rocky debris. So there's several rocky debris, maybe several planets will form out of this. Eventually they start crashing into each other until there's only one planet. This is actually a picture from the Hubble telescope of a solar nebula. And we can't see the star because of all that rocky material. It's blocking the light. This kind of describes how Earth is forming. So, Earth started off as sort of potato shaped, like asteroids. Eventually more planetesimals crash into it. They get larger. It gets this lumpiness. And as more and more planetesimals start crashing into it, that's what these little wispy meteors indicate, the planet gets bigger, it attains more gravity, so it attracts more planetesimals, and eventually it gets spherical. And once rocky body becomes spherical, we can call it a planet, right? A planet or a moon. When they're kind of potato shaped like this, we're going to call these asteroids. So planetesimals accumulate to create lumpy planetoids. The interior heats up to the point of melting. So remember here, because we're converting that gravitational energy into thermal energy. And then we get this spherical planet. And the other thing is that the planet differentiates. So that's where this idea of this gravitational differentiation. So that's this idea where we're seeing the development of the crust on the surface, the mantle, and then the core in the center, right? Gravitational stratification, right? So the strata, remember strata means layers, right? And then we get the core, mantle, and crust. The next question is, how did the moon form? And so remember I talked about how each planet has to clear its orbital distance around the sun. The moon formed by another planet that maybe Mars size or a little bit smaller, and astronomers have called this planet Theia, crashed into Earth, and the core of Theia, the iron core, the differentiated iron core of Theia, and merged with Earth's core. So Earth's iron core is quite large, but then the rocky material of Theia, the mantle material of Theia, started orbiting the Earth, and that coalesced to form the moon. So that's the idea of how the moon formed. Other criteria the moon formed at a different time is that it is actually slightly younger than the rest of the planets. It's about 4.5 billion years old, 4.45 billion years old, compared to the planets, which are about almost 4.6, right? So, so here's another view of how Theia crashed into the proto-Earth, and then the mantle material of Theia eventually coalesced to form the moon around the Earth, right? But that core of Theia merged with Earth's core. And so one way we can look, if we look at the planets, we'll see that Venus and Earth are about the same size, but look how much larger Earth's core is than that of Venus is. All right, so again, following the premise of this chapter, Earth is continuously changing. It's a dynamic planet, and one key piece of evidence for that is all we have to do is look at the moon. When we see the moon, we see craters. We see all these craters, which is a testament to all those planetesimals that were around during the early solar system when they were all colliding with each other, making larger bodies, making the protoplanets. Why doesn't Earth have all those craters? Well, Earth did. But Earth has active plate tectonics, and you can think of plate tectonics as sort of healing that surface. We still can find some craters that are pretty old, some that are over 3 billion years old. But remember, the surface of Earth was so hot and that rocks couldn't really form till about maybe about 4 billion years. So anyways, this is just showing how the early Earth had all those meteor craters, right? So we did have them. And then the atmosphere started changing through volcanic outgassing, right? So the outgassing, one of the main gases that comes out of volcanoes even today is water. So a lot of the water that formed our oceans really outgassed and then precipitated back as to fill the ocean basins here. So let's say a little bit more about this outgassing. When we talk about outgassing, we're really looking at this concept of excess volatiles. So in other words, they do not go into minerals and rocks. So these are primarily the gas, all the gases. And so you can, if you go back to the PowerPoint, you can see that volcanoes primarily outgas water vapor, carbon dioxide, ammonia gas. So NH4 is ammonia and CH4 is methane. Plus other gases like that sulfur gas, hydrogen sulfide, that rotten egg smelling gas, right? And then we see water vapor, condense. When the planet gets cool enough, it starts precipitating to fill the ocean basins. And so most of that water that came out is in the ocean basins, and what remains is primarily carbon dioxide. Remember I said that the early atmosphere was anywhere from 80 to 90% carbon dioxide. And eventually, once photosynthesis began on Earth, organisms started using that carbon dioxide and then started pumping oxygen into the atmosphere. So that's going to change the atmosphere over time. In recent studies, in the last 15 years or so, do point that about a third or maybe as much as half of the water from Earth did come from comets, right? So remember, comets, icy objects, and when they collide the Earth, they can bring water to this planet. So outgassing is a major component, but comets may have contributed some water to this Earth as well. Now, I mentioned something about photosynthesis, right? So some of the earliest evidence for photosynthesis comes from graphite deposits. If we think about what graphite is, graphite's a mineral. So graphite's a mineral, and it's composed of carbon, right? But we know that carbon has several isotopes. There's carbon-12 and there's carbon-13. During photosynthesis, it prefers carbon-12, right? So when we look at the carbon-12, carbon-13 ratio, there is going to be something called a fractionation. So when we look at this graphite, that's anywhere, in fact, the number really is 3.5 to about 3.7 billion years old. 3.5 to 3.7 billion years old. And the graphite of this age shows that that there's an enrichment in carbon-12. In other words, whatever form that graphite picked carbon-12 over carbon-13, and the only thing that does that is photosynthesis. So that's a chemical evidence. In fact, what geologists call this, we call this a biomarker. So there is a biomarker in the carbon isotopes, right? And we call these stable isotopes because they don't come from radioactivity, they're not radioactive. Remember, the one that's radioactive is carbon-14. So carbon-14 doesn't really fit into this equation, right? So, but both carbon-12 and carbon-13 are stable. So here, photosynthesis prefers carbon-12. So if we find deposits of graphite that are enriched in 12, well, what could have done that? The only thing that we know of is something that does photosynthesis, right? So that's the biomarker we use as evidence for when life, at least when photosynthetic organisms started doing photosynthesis on Earth, right? So that began around 3.5 to 3.7 billion years ago. But if you look at the scale down here, you can see that oxygen doesn't really start pumping into the atmosphere until about maybe 2 billion years ago. And really by about 1 billion years ago, it's pretty much close to the level it is today. What was using up that oxygen between 3.5 billion years ago to about 2 billion years ago? And so it took about that time, about 1.5 billion years, to oxygenate the atmosphere. And so there must have been something that as soon as the oxygen went into the atmosphere or into the ocean, it must have taken the oxygen out. So we call those oxygen sinks. And that oxygen sink is really iron. So we have to rust all that iron. And so we have these deposits all over the world, especially here in North America, up in Minneapolis, Minnesota, Wisconsin. We see these banded iron formations, right? So they're composed of metallic minerals, the hematite or magnetite, and then we see this red chert. So chert is a marine rock that forms in the ocean. So obviously this was in the seawater. So we rusted that iron, and it took about 1.5 million years to form these banded iron formations. Well, let's stop here for now.